Let's continue ZEUS training with Section 11, Maneuver Loads Analysis. So the MLODS module computes the transient response due to a pilot input command by invoking the time domain unsteady aerodynamic computation. And as an option, the initial modal displacement and velocity can be selected to excite the aeroelastic system. And prior to the unsteady computation, a static aeroelastic analysis is performed first to establish the initial flow solution. And using the maneuver loads module, you could do that predict limit cycle oscillation. Also, the transient responses that can be selected for output include the grid point displacement, velocity, or acceleration, section loads, grid point forces, modal coordinates, element stress or strain, etc. And the forces and moments at the structural degrees of freedom in terms of Nastran force and moment cards at critical time steps can be exported for subsequent detailed stress analysis. These are the bulk data cards, additional bulk data cards used in the maneuver loads analysis. So we have the MLODS bulk data card, which is the main driver, and then it will refer out to these other bulk data cards, as we'll see. Now, a further note, to compute the inertial loads, it's required to import the GSET mass matrix by the following executive control command as shown here. So we import the GSET mass matrix, which is MGG. And also the plot time bulk data card can be used to output the animation of the deformation or the Nastran force and moment cards at a set of time steps. And this is the bulk data in a relationship for the maneuver loads analysis. So we have the case control section, which refers to the MLODS card. The MLODS refers to the flutter card to define the aeroelastic system. It doesn't perform a flutter analysis. We just use this to pick up the analysis parameters. And then the MLODS refers to the MLD stat, the MLD command, the MLD time, and the MLD print card. So we'll go over these cards. So here's the MLODS card with an ID number referred to by the case control section. Con ID is not used. That's left over from ZEUS. The ZEUS does not allow you to define a control system. That functionality is only available in ZEUS. Next we have the FLUT ID field, refers to a flutter card, which just defines the analysis parameters. Then we have a restart field. This is the identification number of a restart bulk data card to save or retrieve the flow solution of the transient analysis. Next we have the states field that can refer to an MLD stat card, which specifies parameters of the airframe states. Furthermore, the MLD stat can refer to an MLD trim to retrieve the trim solution, which was generated by a trim analysis as the initial flow condition for the transient response analysis. Next, we have the command field, which refers to the MLD command card, which specifies parameters of the pilot input commands for the maneuver. Then we have the time field, referring to the MLD time card to specify parameters of the time integration for solving the transient response problem. And then lastly, the MLD print field refers to an MLD print card or cards specifying the time history of parameters that are to be printed out. The MLD print is kind of unique in that it can refer to multiple MLD print cards all with the same ID. Let's see. So remark 1 is interesting. So for the transient analysis, let's see, we can use this module to obtain the flutter boundary of an aeroelastic system by performing an MLODS analysis at various flight conditions. So by calculating the damping of the transient response at each flight condition, the user can determine the flight condition where the damping becomes 0, which is the flutter boundary. Now, prior to the MLODS analysis, a static aeroelastic analysis is always performed first to obtain the mean flow solution from which the transient response analysis using the time domain unsteady aerodynamic computation of the Euler-Solver module starts. And note that the number of time steps of the static aeroelastic analysis is 100 by default, but you can alter this in the MK param card with the entry TRMN step. And the pressure distribution of the static aeroelastic analysis can be visualized using the plot CP card. And then next, if we want to output loads or forces, we need the matrix KGH. So the ways that you can do that is you can directly import SKGH or AKGH into ZEUS, or ZEUS will calculate KGH from MGH. So if you import SMGH or AMGH, ZEUS will compute SKGH or AKGH for you. And then as a further option, if you don't want to import MGH, you can import just the MGG matrix. So ZEUS will compute SMGH or AMGH based on the phi matrix, the modal matrix, and the MGG that you import, and then it will calculate SKGH or AKGH from SMGH or AMGH. And then the mass and length units involved in the analysis are what we call the analysis units, which are FTM unit and FTL unit specified in the fixed cards. And then also in the flutter analysis, we use all of the flight conditions listed in the fixed MACH, fixed MATM, or fixed MDEN. But in the MLODS analysis, we only do that at one flight condition. So the first value listed in these cards is used, and the remaining values are ignored. Next, we have the MLD command, which defines the pilot input commands. So we have the ID number. Then we have an open-ended input where you can define as many commands as you would like. So the first we have EXT-IMP, which refers to the EXT-IMP bulk data card, which defines where the pilot input command is applied. So this card will then refer to a control surface. Then we have ID tab, which refers to the table D1 card, which specifies the time history of the pilot input command. So if you want to give a doublet to the elevator, you would define the doublet time history in the table D1, and then using the external input, you would refer to the elevator. So this is the external input bulk data card. We have the ID number, the type is not used, and then ITFID is the identification number of an ACTU bulk data card, which is referred to by the AESRF-Z or AES-Link bulk data card. CI is not used, and then label is any arbitrary label that you can apply. And you can also leave it blank if you like. Okay, next we have the MLD time, which defines the transient time steps. So ID time is the ID number. Then we have T start and T end, which is the starting and ending time in seconds. Of course, T end must be greater than T start. Then we have DT, which is the time step. Out DT is a skip factor for the output, so only every out DT time steps will be saved in the output, and the default is 1. So if you have a very small time step, for example, 1000 hertz, so 0.001, and you only want to output at 100 hertz, you can specify out DT of 10. Then we have a print flag. The default 0, we output numerical values of the time history on the standard output file. If print is negative, then we suppress the output. Next we have a method. This is an integer flag to select the time integration method for solving the state space time equation. We'll see that on the next slide in the remarks. Then we have the mode 0 field. This is an identification number of a set 1 card, which lists out a set of mode indices. And the generalized coordinates of these modes during the transient analysis are forced to be 0. So during the solution, we do not apply the forces back to those modes to see how those modes deform. Those modes are just held at 0. And then we have an open-ended input where we can specify initial values for our modes. So we have a mode, which is the index of the structural mode for which the initial value is specified. And then we have X, X0, V0, and G0. G0 is not used. X0 is the initial displacement, and V0 is the initial velocity. So we can have no modes or as many modes as we would like here to specify initial conditions. And this, you would use this to kick the system if you want to give an artificial kick to excite the system to see what the response would be. Now we'll talk about the time solver method. So for method equals 0, the discrete state space equation is solved by this equation, where our A and B matrices involve the structural generalized mass, stiffness, and damping matrices. X are the states, U is the generalized aerodynamic forces, and N is the index of the time step. For method equals 1, then we use this equation for the discrete state space equation. So method equals 0 is the default. And then why would you want to set the modes to 0? If the rigid body modes are included in the transient analysis, the rigid body modes may diverge. We can just hold those rigid body modes to 0. Now note, this is different than deleting the rigid body modes using the MList entry in the Flutter card, because deleting the modes using the MList will completely remove those modes from the transient analysis. But by leaving the modes in the analysis and then just holding them to 0, this will keep the influence of the rigid body modes to the elastic modes for the transient analysis. Next, we have the MLD print card, which allows us to output parameters of interest to a data file. So we have ID print, which is the identification number. File name is the name of the data file. And then form, we have table for just the XY tabular output, IDEAS, FEMAP, and ESA. Then the PSD is a character string, either time or PSD. So time is the default. This is for the time domain response. PSD allows us to output the power spectral density versus frequency. Then we have TS PNT and TE PNT. These are the starting and ending times for the printout. SOF is a flag character string. It can be either yes or no. For SOF equals no, the forces and moments and the component loads are computed using the mode displacement method. For SOF equals yes, then the mode acceleration method is used. And then we have an open-ended input, label, and ikey. So label is a character string, and ikey is either a character string or an integer, and these define the parameters that we will output due to the transient maneuver. Let's see. So for the SOF option, that's explained in remark 3. So the equations of motion of the transient response reads k times x equals minus m times x double dot minus c times x dot plus fa of t plus fe of t. Fa is the aerodynamic forces, and fe are the external excitation forces. So the mode displacement method computes the forces at the structural grid points by F equals k times x. And the mode acceleration method uses the summation of forces. So F is equal to minus m times x double dot plus Fa of t plus Fe of t. It's believed that the mode acceleration method is more accurate than the mode displacement method. However, the drawback of the mode acceleration method is that the forces due to structural damping cannot be included because the damping matrix is normally not available. And then these are the parameters that we can output using the MLD print card. So we have state, which is airframe states. So I key is the character string that matches one of the airframe states. D state is the time derivative of the airframe state. And then modal X is the generalized modal coordinates. And I key is an integer, which represents the mode number. Modal V is the time derivative of modal X, and then modal G is the time derivative of modal V. And then modal XVG will output the modal displacement, velocity, acceleration in the output 4 format on an external file. So I_key is an integer that refers to an ext file, bulk data card, which defines the name of that file. And the matrix stored on the file in the output4 format is shown here. So we have Cc and delta, then we have Cc dot, delta dot, and then Cc double dot, delta double dot, all for the first time step, and then we move to the second time step. Next we have append, which is the same as modal XVG, but it appends the data onto the already existing file. Next we have grid xt1. This is for the displacement along the x direction at a structural finite element grid point, where I_key is the integer of the identification number of the grid point. And then xt2 and xt3 is for the y and z directions. R1, R2, and R3 are for the rotational degrees of freedom about the x, y, and z axes. Then we have grid V. So grid V is the derivative of grid X. And of course we have T1, T2, T3, and R1, R2, R3. Then we have grid G, which is the second time derivative with respect to X. Moving on, we have force. So force T1 is the force along the X direction at a structural finite element grid point, where I_key is the integer that represents the identification number of that grid point. And remember, for the forces, you must import the KGH matrix. So then force T2 and force T3 are for the y and z direction. And then we have force R1, R2, and R3 for the moment forces about the x, y, and z directions. Next we have load mod, which refers to a load mod bulk data card. So I_key is the integer matching the ID number of the load mod card. So this is for measuring component loads. And once again, we must have the KGH matrix available. Then we have DMI. This is for any parameter whose modal values are imported by the DMI bulk data card. And I_key is a character string which matches the name of the matrix on the ZEUS runtime database. So that matrix can be specified by the DMI bulk data card or the assign matrix executive control command. So these modal values can be stresses, grid point forces, strains, etc., and can be obtained from the free vibration FEM analysis. And then lastly, we have PCH file. This is for structural parameters defined by the PCH file bulk data card. So I_key is an integer representing the identification number of the PCH file bulk data card. Lastly, as a note here, we provide in the ZEUS installation directory in the miscellaneous folder a Windows application called zarma.exe. This executable can load a MLD print output file and plot the results, and then also calculate the frequency and damping content of selected responses using the autoregressive moving average methodology. So the form must be set to table in order for Zarma to be able to read the data. Next we have the MLD stat card, which defines the airframe states. So ID stat is the identification number referred to by the MLODS card. ID trim is the identification number of an MLD trim card to retrieve the trim solution generated by a trim analysis as the initial flow solution for the transient response analysis. Then we have these remaining fields here are left over from ZEUS, so they're not used in ZEUS. Then we have our state and initial. This is an open-ended input. So state is a character string which matches one of these following airframe state characters. For symmetric maneuvers, we can have X, H, U, W, alpha, theta, or Q. For antisymmetric, we have Y, beta, V, phi, psi, P, and R. And then for asymmetric, state can be any of the combined. And then initial is the initial value of the state. So this is used for converting the rigid body modes to airframe states. And that conversion is done as follows here. For the symmetric maneuver, the MLD stat card constructs this transformation matrix. So this transformation matrix converts the airframe states to the rigid body states. So as an example, if we look at TZ dot, the rigid body state TZ dot, that is equal to minus V infinity times alpha plus V infinity times theta. If you select W instead of alpha as your airframe state, then TZ dot is minus W plus V infinity times theta. And then for the antisymmetric maneuver, the transformation matrix is shown here. So this transformation is this step converting the rigid body degrees of freedom in the body axis to the airframe states. ZEUS will do this conversion, the principal axis to rigid body degrees of freedom, when you specify the support entry in the assign FEM. Let's see. So our states are defined here. So theta is in radians, alpha is in radians, Q is in radians per second. And similarly, phi, psi, and beta are in radians, and P and R are in radians per second. Remark 6 is important. If a steady state trim condition is desired at the initial time, then the initial values of the airframe states can be obtained by performing a trim analysis. To satisfy the steady state trim condition at an initial time, it's recommended that alpha initial equals theta initial, so that TZ dot initial equals 0. If you specify alpha not equal to 0 and then theta initial equals 0, this will give an impulsive increase because TZ dot will be non-zero, which is not a steady state trim condition. And for an antisymmetric condition, B initial equals minus Y initial is recommended. Next we have the MLD trim card for the initial trim condition for the transient response. So we have ID trim referred to by either the trim card or the MLODS card. ISTFLW refers to an EXT file card, which specifies a file name where the flow field solution of the trim condition is stored. FILTRM is an ASCII file which stores the trim solution in the output 4 format. FILDEF is a file name of an ASCII file that stores the deformation at the trim condition in the output 4 format. And then FILLOD is a file name of the ASCII file that stores the inertial loads at the trim condition in the output 4 format. So the MLD trim card can be referred to either by the trim analysis or the transient response analysis. So for the trim analysis, the trim results are stored on the file, on these files. And then for the transient response analysis, the maneuver loads, the data on this file is retrieved and used as the initial trim condition for the transient response analysis. So in practice, you'd want to have a trim analysis and an MLODS analysis in your same input deck, and then they can both refer to the same MLD trim card, and ZEUS will do the correct thing. When it runs the trim analysis, it will save the data, and then when it runs the maneuver loads analysis, it will retrieve that data that it saved in the first run.